Good morning, champs. Today we are going to solve another static friction problem. But this time, friction is supporting an entire rigid body rather than a block on an inclined surface. A uniform horizontal bar rests against a rough vertical wall. A cable connects the bar to a point on the wall above it. Our goal is to determine where along the bar the cable may be attached so that the bar does not slip. The bar has a mass of 1.6 kilograms and a length of 1.2 meters. The coefficient of static friction at the wall is 0.4. Because we are looking for a range of possible attachment positions, we should already expect two limiting cases. We begin with the free body diagram of the bar. The weight acts vertically downward at the center of the uniform bar. The cable exerts a tension at the attachment point. At the wall, we have a normal force acting horizontally and a friction force acting vertically. At this stage, we should not assume whether friction acts upward or downward. Static friction acts in whichever direction is required to oppose the impending motion. And in this problem, that direction can actually change depending on where the cable is attached. Next, consider the cable geometry. The horizontal distance from the wall to the attachment point is x, while the vertical distance to the upper cable support is equal to the bar length. We could calculate the tension magnitude and its angle, but there is an easier approach. We will work directly with the horizontal and vertical components of the tension. We begin with moment equilibrium about the contact point at the wall. This is a useful choice because both the normal force and the friction force pass directly through this point and therefore produce no moment. The vertical component of the cable tension acts at distance x from the wall. The weight acts at half the bar length. Moment equilibrium gives the vertical cable component equal to the weight multiplied by the bar length and divided by 2x. Now apply horizontal equilibrium. The normal force must equal the horizontal component of the cable tension. From the geometry of the cable, the ratio of the horizontal tension component to the vertical tension component equals x divided by the bar length. Substituting the vertical component we just determined produces a surprisingly simple result. The horizontal cable component equals 1/2 of the bar's weight. Therefore, the normal force at the wall is also exactly 1/2 of the weight, independent of where the cable is attached. Now apply vertical equilibrium. The friction force plus the vertical cable component must balance the weight. Solving for friction gives the weight multiplied by 1 minus the bar length divided by 2x. This equation reveals something important. Depending on the value of x, the friction force can be positive or negative. In other words, friction can act either upward or downward. First, consider what happens when the cable is attached very close to the wall. A small value of x requires a large vertical cable force to produce enough moment to support the bar. Eventually, the vertical cable force becomes larger than the bar's weight, so the bar would tend to move upward at the wall. Friction must therefore act downward. At the lower limiting position, the downward friction force has reached its maximum static value. Applying this limiting condition gives the minimum cable position equal to the bar length divided by 2, plus the coefficient of static friction. Using our values gives a minimum distance of 0.5 meters. Now move the cable attachment farther away from the wall. The required vertical tension becomes smaller. Eventually, the weight of the bar tends to make the bar slide downward, so friction reverses direction and acts upward. At the upper limiting position, the upward friction force reaches its maximum static value. Applying this second limiting condition gives the maximum attachment distance equal to the bar length divided by 2 minus the coefficient of static friction. Using our numerical values gives 0.75 meters. Therefore, the cable can be attached anywhere between 0.5 meters and 0.75 meters from the wall while maintaining static equilibrium. The most important lesson from this problem is that static friction does not have one predetermined direction. Its direction depends on the motion the body would undergo without friction. If the cable is attached too close to the wall, friction must act downward. If the cable is attached too far away, friction must act upward. Between those two limiting positions, static friction adjusts to whatever value is required to maintain equilibrium.